Okay. So that video player has to go into your hard drive, has to find the video you want to play. And then remember from my lecture about binary, videos are pretty big files, because if you think of a video, and what is a video? It's a bunch of frames. So if you have a video with 60 frames per second, that means every second there is a picture stored somewhere. And depending on the fidelity of the video, it could be a big, big, big file. So your program has to read in the file. That's not really done. Well, that is actually done with an algorithm. Where I'm going with this is that algorithms are like, you can think of them as the heart of a program. It's information that passes through a program, can be put in and put out in many different ways, but at some point it has to pass through the logic of how that information is digested. So if you have a really crappy video player, it'll have a crappy algorithm. It'll load your videos really slowly, something like that. But if you have a really good video player, then it'll read in your file, it'll play the whole video with beautiful quality, no issues whatsoever. So the heart there is what governs the efficiency of the program. So that's actually what we're going to be talking about today, algorithms. Now, off the top of my head, algorithm, pretty sure comes from an Arabic mathematician and like polymath from like the 1300s, whose name was like Al-Khwarizmi or something. But Al-Khwarizmi, algorithm, you can see where the relationship comes from. But this is a concept much older than computer science. But I'm going to be talking about it within the realm of computer science. So first, we have to ask ourselves what an algorithm is. So an algorithm, as defined by, I literally just Googled this and found this is the Wikipedia definition. So an algorithm is a finite sequence of well-defined instructions typically used to solve a class of specific problems or to perform a computation. Algorithms are used as specifications for performing calculations and data processing. So an algorithm is essentially a set of instructions. When we're taking in data, or if we are navigating a huge pile of data, how do we find things quickly? Or how do we sort things quickly? Or those are really the two big ones. How do we find things quickly? How do we sort things quickly? Those are the two really big questions when we look at algorithms. Now, within computer science, it's not like an algorithm it's not like a program you download. Like, oh, I want to use bubble sort algorithm, and I'm going to go download the bubble sort algorithm from the internet. It's a set of instructions that you yourself write if you're writing software. So,
is it like a recipe? Kind of recipe?
I was going to make that analogy. It's like a recipe out of a cookbook. When you're baking a cake, you could bake a cake in your kitchen. I could bake a cake in my kitchen. And we'll probably use pretty much the same ingredient. Like if we're baking, I don't know, like a vanilla cake. Maybe you go to the store and you get like the Whole Foods brand vanilla. I go to the store and I get Trader Joe's vanilla. Maybe the portions are slightly different. But at the end of the day, even though we're using different equipment in different kitchens, using different ingredients, we're both making a vanilla cake. So the set of instructions for making that cake are going to be very, very similar. So that's an excellent analogy that you draw. Yeah. So what does an algorithm do? Well, that's where the magic trick comes in. I actually don't own a deck of cards. Come on in. Oh, hi. So let's see. I actually don't own a deck of cards. My friend, I'm borrowing these from a friend. Just like a brand new shiny deck of bicycle cards that I need to very quickly shuffle. So what does an algorithm do? Let me show you using some cards. So why am I using cards? Well, remember what I said. Algorithms are used for navigating through big piles of data. Let's say we have, I don't know, we have a list with 1 million people in it, and we want to very quickly find a person in that list. How do we find that person without just, looking through every single person in the list? Find their name, right? Yeah. But if there's a million people, it can be hard, even for a computer, right? What if there's a billion people? Or what if we're trying, or think about how this problem can grow. What if we're trying to find, let's say, like 2 degrees of connection from a person? So say we have one person like myself, and we want to see if you were to make a network of everybody that I know and then everybody that those people know, how big would that network be, and how do you find all those people? So that can be a pretty big problem, especially in Facebook, for example, where there are so many users on the platform that they have to, okay, this is very hard. I think because these cards are new.
But I know how to shuffle.
You know how to shuffle? If anything, I might just hand these to you. Actually,
You did a good job.
no, you don't do it. Go ahead, shuffle these for me. Yeah, it's hard. They're like slippery. It's like they're greased up or something. Let's see. Yeah, I was in scouts, so do you see what I mean? Okay, yeah. See, but the end is easier than the beginning. But they, I was in Boy Scouts, so we would like, we couldn't have like our phones at the campsite, so we just play a bunch of card games. So that's where I learned how to shuffle. I'll let you shuffle that one more time, and then I'll just. Okay, cool. I think that should be good.
Yes.
Cool. Thank you so much. So let's go ahead. Let's pull out. This is perfect. We got these cards. I'll throw in a jack. I'll throw in a 7. How many is this? So this is, let's see, 1, 2, 3, 4, 5, 6, 7. I need one more card. We'll throw in a 9. Okay. So I'm gonna go ahead. I'm gonna sit over here. I'm gonna pull the show. I'll move this monitor over. Okay. So let's say I have 8 cards. So you have a king, a 10. So I have a king, a 10, a 2, an ace. These are my 8 cards. A 4, a jack, a 7, and a 9. A king, a 10, a 2, an ace, a 4, a jack, a 7, and a 9. Now to start, these are. So to start, these are not in order, right? So there's different ways I can put them in. And if any one of you picks up this set of cards, you're not going to sit and think about what algorithm you're using to start, putting them in order. So I'm going to approach this using the different algorithms I'm going to teach you guys. So the first approach I can do is called bubble sort. So watch what bubble sort does. I'm going to just keep going and going from the beginning to the end of the list or the set of cards, and I'm going to do one specific operation. So I want to sort it so the smallest cards are here and the largest cards are here, without looking at their seats. So first, I'm going to look at 2 cards at a time, and if I see that there is a bigger card before a smaller card, I will flip them. So here I saw there was a king and a 10, so I flipped them, so now there's a 10 and a king. Okay, let's move over. Now I see there's a 2 and a king, so I flip them, and now, cool. Ace and a king, I'm going to consider ace to be 1. Here.
Okay.
Yeah, so here,
That could go either way.
it could go either way, yeah. So here we'll say ace and king, and notice, inevitably, I'm going to just keep bumping the king up to the top. Because king is the highest. So here, jack and a king, and then you go 7 and a king, then we go 9 and a king. Now, the beautiful thing about this, I know for a fact this is where it should be. So this king is where it should be. This is the highest card I have. If there was another king in here, I would have to do it again. But okay, let's try this process again. These 2 cards, 10 and 2. Let's flip them. Okay. 10 and ace. Let's flip them. 10 and 4. We'll flip them. 10 and jack. It doesn't stop. We just don't do anything. So here, we don't have to do anything. 10 and jack, they're in order. Now let's move on. Jack and 7, we need to flip these. Jack and 9, we need to flip these. These 2 cards are exactly right. So I'll go ahead and I'll do this one more time, and I think at this point you'll get the idea. So 2 and ace, we flip them. 2 and 4, we keep them the same. 4 and 10, we keep them the same. 10 and 7, we flip them. 10 and 9, we flip them. And now these 3 cards are exactly what they have to be, right? So we would just do this over and over and over again until eventually we would have ace, 2, 4. Oh,
And it's in order.
it is actually in order. That's a funny part, I didn't really notice that. So yeah, that's called bubble sort. It's called bubble sort because you can envision the 2 cards you're looking at a time exist in a bubble. So we look at this bubble, this bubble, this bubble. If this bubble is good, ignore it. Then we move on to the next bubble. If we need to flip them, we flip them. So you can see I had to do a whole bunch of things. It's not a very intuitive way to sort cards. And the other thing too, this is 8 cards. Imagine if I pulled out all 52. I'd be sitting here for hours doing this, and nobody would want to see me do that. I'd have to do this process. I would have to go through every list, or I'd have to go through the entire deck 52 times. And within each of those times, I would have to do a whole bunch of flips. Okay. So let's try one more method. This is called merge sort. So I just put these in a random order. So this one is called merge sort. So how merge sort works is a little bit different. So merge sort, we're going to be a little bit more clever. So here, let's do 10, ace, king, 9, 4, 2, 7, jack. Okay. So let's be a little bit more clever about this. And it's going to allow us to process more of the deck at a time. So 10, ace, king, 9, 4, 2, 7, jack. So here's what we're going to do. We are going to split this deck twice. So first, let's split it up into these 2 halves. So we have 10 and ace and king and 9. Or we have 10, ace, king, 9. And then we have 4, 2, 7, jack. Okay. So we split them up. So you know what we're going to do next? We're going to split them up again. So now this subgroup, let's split this up into 2 smaller groups. So now we have a 10 and an ace, and a king and a 9. So finally, we stop the splitting once our groups, our smallest subdivisions, are either a size 1 or 2. So we're going to be splitting up this whole thing. So this is going to get turned into this, right? And move this over. Yeah. So this is what it's going to end up being. If we have 9 cards, there would be 1 card by itself. So then the easiest list in the world to sort is a list of size 2 or 1. If you have a list with only 1 thing in it, it's in order. If you have a list with 2 things in it, all you gotta do is this. Are they in order? Yes or no? Okay, well, we consider the ace to be a 1. No. So we flip them. So to flip these guys too, and these guys, and that stays the same. So now what we're going to do is we're going to merge back up. So we split apart into smaller groups, and we're going to merge back up. So first we start with these 2 groups. So this right here. Let's move them around to look like this. So we have ace 10 and then 9 king. So I'm going to just grab the card in front of me that's smallest. So ace, and then 9, and then 10, and then king. So it was almost like a conveyor belt. I saw 2 conveyor belts of cards coming in. I just grabbed the card from the belts that's smallest and put it on the list. So here now we have 9, we have ace, 9, 10, king. So now let's go ahead and we'll put them in that order. So the beautiful thing, this whole thing is sorted. We know that for a fact. So now let's go over here. So let's make it like a conveyor belt. So I'm going to grab the smallest thing in front of me. So it's a 2, and then it's a 4, and then it's a 7, and then it's a jack. So then we arrange them just like that. So now these 2 halves are in order, but we're not done. We can't just put them together and be done with it. These guys are in order, but we need to then combine them. So let's make it a conveyor belt one more time. So ace, 9, 10, king, 2, 4, 7, jack. So we're getting the conveyor belt. So we'll go ace, and then the smallest thing here between 9 and 2, 2, and then 4. We'll put them over here. And then 7, and then 9, and then 10, and then jack, and then king. You think of it as a conveyor belt, you just keep grabbing the thing. If it turns out this conveyor belt has all the smallest cards, you're going to grab everything out of here. So that's merge sort. It's a little bit more confusing. Bubble sort, you just look at a bubble. I mean, the bubble sort, you just look at a bubble and you flip those bubbles around. It's easy, but it's not efficient. This is more complicated. And my ability to even like sit here and do this to you has taken years of training. To even like remember the steps that goes in the merge sort is kind of tricky. But if you think about this like a computer, if we had millions of cards in front of us, think about the nightmare that bubble sort would be. Because now we'd have to look at the entire set of 1 million. We'd have to look at that a million times. So that we could get the card at the end of the order. Here, we have 1 million, and then we split them up into 2 subgroups of 500,000 each, and then 250,000 each, 125,000 each, something smaller than that. And we just keep going and going and going until finally the little subgroups are either 1 or 2. And then we flip, and then we start doing the conveyor belt thing, reassemble it, and ultimately that will take us less steps than bubble sort. Even though it's harder to think about, it takes us less steps. So that's my card trick. Now I'm going to show you what those algorithms actually look like in action. So, before we even do that, though, allow me to explain why it's important. Oh, so in summary, it's essentially a clever set of instructions to sort or navigate through data quickly. And there are varying degrees of cleverness, and people literally devote their lives studying this field, right? You have at pretty much every important institution studying computer science, you have a department looking at nothing but algorithms. So they're almost like, you could almost consider them to be closer to mathematicians than computer scientists, right? Well, I mean, they're computer scientists, but they're more on like the theoretical side of things. So it's a clever set of instructions to navigate or sort through things quickly. And your cleverness can range from anything between bubble sort, which is something you learn in like sophomore year of high school, if you take a computer science course, all the way up to the most insane hash function, triple binary, whatever, like just like insane things, but they save you a lot of computational time. It minimizes operations needed to complete the task. So if we have a set of 1 million numbers or 1 million cards, we're looking for the way with the smallest amounts of steps to get what we want. So to speak, it's the quickest way to bake your cake, right? It closely follows a set of instructions. So algorithms are not equations, they are rule books. And when you code those rule books in a program, you have to be very, there's not really a whole lot of leeway for exceptions or things of the sort. You make that set of instructions and then you will conform you make the set of instructions and then the program will follow the set of instructions. And there's not a whole lot of leeway there. So this is important because time is money. So I mean, on this slide, you can see a whole bunch of really big tech companies, right? You have Google, Facebook, Apple, Netflix, Grubhub, Uber, Microsoft, I mean, you name it, right? These are like, 20 years ago when we looked at companies with the largest market shares, you had companies like Johnson & Johnson, like different, companies that sold commodities, right? Now, the giants are tech for different economical reasons. But one thing is, all of these guys place a lot of importance on algorithms. If you want to get a job, and believe me, I know, if you want to get a job with any of these guys, you know how they test you? If you want to be a lawyer and you want to get a job, what do they do? You go to law school, but then when you're done with law school, what do you have to take? Bar exam. Thank you. You have to go get the bar exam. You have to pass the bar exam in order to be licensed to practice law in a state. So this isn't a bar exam. Bar exams are much harder than this, but these are still really hard. What these companies will do, if you want to work for them, they will give you multiple interviews. I'm talking like upwards of 10 to 15 interviews with nothing but algorithm stuff. So they will sit you down and they'll say, here's a list of 1 million numbers. Put them in order in this amount of calculations. So if you sit down there and you do bubble sort, they won't let you. You need to do something clever. And that example I gave is actually really simple. Sorting numbers. These guys will give questions like, for example, if you have 2 sentences or if you have 2 words, calculate the amount of additions, subtractions, and substitutions it takes to change one word to another. So what I mean by that is take the word dog and what? Bone. Okay, so they don't share, okay, they share one of the same letter. So you have to replace the D with a B, you have to replace the G with an N, and then you have to add an E at the end. So dog, you have 3 calculations. Or if you have the word like, I don't know, cat and cot, as in C-O-T, you just have to switch the A to an O. But then say you have the word like guarantee and demand. There you have a bunch of different operations. How do you even calculate that? That's with stuff like this. Now, that's how you get a job at these companies. And the reason it's so important to these companies. Let's take someone like Google. So when you look up something on Google, you type in your search query, it's going to take Google a fraction of a second to give you billions of results. That's kind of their thing. That's why they've made so much money, is because you look up vanilla cake recipe. It will take them a microsecond to find you a billion vanilla cake recipes. How do they do that? Because think about what it is they're pulling through. When they bring you all those recipes, they're looking through the entirety of the internet, or as much as they can see. So how do they take this gigantic pile of information and condense it down to fit what you're looking for? They can't bubble sort through that information. They can't go, well, this is a cake recipe and this is not a cake recipe, so we're going to flip it. They don't have time for that. There, time is money. If you're looking through, if let's say Google was only dealing with 10 websites ever, there was only 10 websites on the internet, it would be really easy. They probably wouldn't even need an algorithm. You know, like if there's 10 websites on the internet and you ask for one of the websites, Google will take half a second to tell you, there's your website. But if you have 1 million websites and you ask Google for one of those websites, if you use something like bubble sort, it can take them 1 trillion calculations. That's with 1 million. We know there are billions. So there, at that point, I think you hit like 1 quintillion calculations if you do this wrong. So time is money. Time is money. And since algorithms govern speed, that's why they're so important. Yeah.
Now, a while back, personnel technology, when you submit a resume or a cover letter or something like that, I was always told that there are keywords that they would look for.
Yep.
Do they scan these resumes and use information somewhere and then target those keywords? Can you explain that to me?
Sure. So that is, it's a little different from this, but yes, they do that. So when I was an undergrad, I would go to my college's career center. God bless those people, by the way, seriously. They like helped me write my resume and like all my cover letters, all those. They helped me get into Cornell. Kind of. Actually, no, I did Cornell myself, but the internships I got, they helped me get into. But regardless, what happens when you submit a resume nowadays, it depends on the company. But say you submit a resume to, oh my God, I didn't include Amazon. I knew someone was missing. I didn't include the biggest, evilest one. That's kind of funny. My bad. Okay, well, let's say you submit a resume to Amazon. So there, depends on the role. Let's say you're submitting to be a software engineer. That's like That's like the grunt of it. Well, the grunt is the warehouse workers, but like I'm saying, within the core company. So let's say you submit to be a software engineer. They probably get upwards of maybe 20 to 30,000. I would guess maybe 20 to 30,000 software engineering applications per year. So the truth is, with the computers that they have, even if there's 20 to 30,000 resumes, that's not that much to look through. So algorithms like these aren't going to be as relevant. But there are different types of algorithms called machine learning algorithms. So we have algorithms that are just doing one thing. They're looking for a name. They're navigating from point A to point B. That's the algorithms I'm talking about today. You also have machine learning algorithms, which are different. The algorithms I'm talking about today have like one set of rules. They always follow that set of rules. Machine learning algorithms, the whole point is that they can change their rules on the fly in order to adapt themselves to a situation. So here's what Amazon did. They tried, I think in 2015 or 2016, they tried using a machine learning algorithm. So if you submitted your resume, it would look at a list of the people who had successfully gotten jobs at Amazon. So you submit your resume to Amazon, and it's going to look at everyone who's previously gotten a job at Amazon. And that's how it gets the idea of what a successful Amazon applicant looks like, right? Here's the problem with that. If you look at the demographics for who works at Amazon, can you guys guess what the main, so, all right, let's be real here. What race do you think is most represented at Amazon for software engineers?
Asian.
White.
And what capacity though?
White. Well, okay, so first, I'd like to ask you, if you took every software engineer, every programmer at Amazon, most of them are white. So that's one thing. Another thing, which sex do you think they are? You think they're male or female?
Male.
Yep, all of you guys in unison said that. Fun fact, software used to be a female-dominated field. I actually might talk about that during one of the lectures. But there was this whole thing in the 70s and 80s that caused a shift. But yes, so successful Amazon employees, white, male. That's actually pretty much it. So this is what ended up happening.
30 years old.
Oh yeah, like 20, 30 years old. So if you're applying as like a 50 or 60-year-old, then so this is what ended up happening. So they tried one of these algorithms where you would submit your resume, and then the computer came up with a set of rules for what good applicants looked like. But it did that by looking at who had already gotten in. So now it was biased. To the algorithm, the best employee, and I'm not kidding, the best employee for Amazon was white. So they had a white sounding name like John Smith or
Came from California.
from Jones or Jones, something very, yeah. So if your last name ended Sanchez or Ferrero, they would dock you points. I'm not kidding, they had a point system. If you had certain adjectives or if you had done certain technologies, you would get points. If, and I am completely serious when I say this, if your resume said that you were a woman, so for example, say you go to Harvard, you're a woman who goes to Harvard and you're the captain of the rowing team, and you're a software engineer, like you study computer science, you're the captain of the I don't know if there's a female rowing team actually. Is there? Whatever. You're the captain of the female cross-country team, okay? Really, really like a big shot at Harvard. In this algorithm, if you said women's cross-country team captain, it would take points off. So,
Why?
because you're a woman.
Oh.
Successful applicants were men, so clearly you're doing something wrong.
Oh.
So that's how the machine learned.
And
Yeah.
like you said, with the name, I remember when I was working, I had friends that were applying for jobs, and they were African Americans and their names, and I told them, I said, guys, I'm going to be.
Yep.
I'm gonna get the
Yep.
job.
There have been studies.
My name.
There have been studies, and not even like studies involving computers. Like, oh, how does a computer see a name that's typically considered African American? It's like, how does a human recruiter, even human recruiters, show bias?
Yes.
So if your name was Tim Smith, you would be let in more often than if your name was something more, I guess, ethnic sounding.
Mhm.
So like when I was applying to back in September when I was applying for work, or actually that was actually a year ago, senior year of college, when I was applying to jobs, I have an uncle who lives in Ecuador, and he told me, change the spelling of your first name. If you look at the spelling of my name, Agustin, Agustin, that's a Colombian spelling. He told me to change it to, you know, the city in Florida, Saint Augustin. He told me to change it to that, so that they let me in more often. But that's machine learning algorithms. We're looking at like data processing algorithms, but that's big. And actually, I want to do, for like the Wednesday lectures, I want to do one on women in computer science and like the story of how they got kind of screwed over. And also ethics. Ethics is huge and not talked about enough. That's something that will come up during ethics.
That's good, yes.
Yeah. So,
Okay.
yeah, so let's learn some algorithms together. So the first one, I already showed you guys this with the cards. The first one we're going to look at is bubble sort. So I tried my best to convey this on the slides. I really hope I did a good job, but we'll see. So let's start with this list right here. This, I just generated it randomly using a program. So we have 4, 16, 7, 0, 13, 2, 20, and 2. This list is not in order. We want to get it in order. So in order, I think it would be 0, 2, 2, 4, 7, 13, 16, 20, right? So let's look at how bubble sort would do this. So bubble sort is going to take a few steps. We have like the dramatic. Where is that movie from? That's like, I feel like I'm in like a Victorian drama. I'm about to
A novella.
a novella or something. Oh yeah, I mean there's like a church right here, so. Yeah, I came here for lecture, not Jane Austen novel. Okay, so we're gonna do this process. This is not complete. So before I get into the details, look, we start here and we end here. From this, we call this a step. So this whole thing is one step, and we successfully got the 20 in order. Now 20 is correctly sorted. So from this one step, we got 20 in order. So now, how did I do this? Well, we start with our list, right? And can you guys see the screen up here? Okay, there's okay. So first we start, and so to explain it, so we want to look at 2 numbers at a time in the list. And if the 2 numbers are not in order, all we do is flip them. So what that means is, here we see 14, this would be 4 and 16. Good. 4 is smaller than 16. 16 and 7, we have to do something about them. So we take the 16 and the 7 and we flip them. So now it's 7 and 16. So 16 and 7, we flip another 7 and 16. So now let's take a look at this. 16 and 0, we flip and it becomes 0 and 16. Then 16 and 13, we flip, it becomes 13 and 16. It's the 16 that keeps getting pushed, right? Because it's big, so it keeps like winning, right? So then 16 and 2, it flips, becomes 2 and 16. Then 16 and 20. That's fine. We don't need to do anything about that. But then we go, when we look at 20 and 2, then we need to flip that. So now it's 2 and 20. So from this whole process, this is called one step. And in this one step, we have successfully sorted one number, which is 20. We know for certain that this guy is in the right place. Cool. Okay. Then we do it again. So now at the top here, this is the same list of numbers at the end of the previous step. Same list of numbers, we've done some flipping. Notice the 20 is where it should be. So now we start. 7, 4 and 7, okay. 7 and 0, we have to flip. 7 and 13, okay. So 13 and 2, we have to flip. And then we get 13 and 16, that's fine. Then we get to 16 and 2, we have to flip. And at this point, we have 16, we already know the 20 is where it should be, so we don't even need to look at that. But now we know for sure the 16 is where it should be, and the 20 is where it should be. So this has been step 2, right? So I think the next slide is like I challenge you guys to try to, yes, okay. So let's see if you guys can do the next step. So we have this list of numbers. So what is our first step going to be? Does anybody know?
And the first one.
0, 4. Yeah. So what's wrong with this? Yeah. So 0 and 4. We have to flip it, right? Yeah. So now I feel like we're at the circus. Oh my gosh, should I screw that up?
Flip it. What's wrong?
Oh,
What happened?
that's me.
Are you tired?
A little bit. Okay. So hold on. I can change that literally. Hold on. Let's say if I change this, this should be 0. This should be 4. Okay. We're just gonna pretend this is what it always looks like. And let me make sure that it's sharing the right. Yeah, honestly, I have no idea what you're talking about. There's always something right. I had it right. Yeah, so 0 and 4 becomes 4. And then, okay, so I screwed this up a little bit, but you guys got it right. So we would then move 13 and 2 would become 2 and 13. And then finally, at the end of this, we know for a fact the 13 is sorted correctly. Yeah. So that's bubble sort. So here are some facts about bubble sort. So the bubble sort is 0, sorry, a little tired. Bubble sort is O of n squared, time complexity. Now time complexity is a part of computer science. To be very clear, computer science is it's like a clown or like something like that. Anyways, computer science isn't just programming. It's actually the interplay between programming, mathematics, and ethics. Those three. So programming, mathematics, and ethics. So when we say something like this, we're talking more about the math side of things. So what do I mean by this? So time complexity is an entire like subset of computer science. And again, people spend their whole life studying it, which basically says with a certain algorithm, how long in the worst or best or average case scenario will that algorithm take? So when I say O of n squared, this is what we call worst case time complexity. So what do I mean by that? This means in the absolute worst case scenario for our problem. So remember, our problem is we want the list to be smallest to largest, right? So does anybody know what's the worst possible list to start with if we want smallest to largest? What's the worst list we could start with? 1. No, not quite. If the worst possible starting position would be the opposite. So if we had a list that was largest to smallest, it will take the longest to sort with bubble sort. So think about it. Here, we were actually able to skip a few steps. So like, for example, here, we were able to skip over this because this was already in order. But if the entire thing was largest to smallest, every step, we would have to flip, repeat, flip. So you'd have to flip a bunch of times. So ultimately, with the absolute worst possible starting, that is to say, with a list that is largest to smallest, we need to take n squared operations. So an operation could be a few different things. In our case, it's a flip. So that means with bubble sort, for example, if we have 1,000,000 numbers, it's going to take 1,000,000 squared operations to compute. 1,000,000 squared is 1 trillion. So that means on a computer that you could buy for maybe $800, $900 today, it would take your computer about 2 seconds to do this. If it has 5.0 gigahertz of processing power. Doesn't sound like a lot. 2 seconds. 2 seconds to take this list, flip it a whole bunch of times, and then spit out a sorted list. But that's with only 1,000,000 numbers. What if we're Facebook and we're looking at billions of people? Then we get into quintillion operations. And that's not gonna fly. Even like a 2-second thing, if someone types in something on Facebook and it takes 2 seconds instead of 0.2 seconds, the user can get pissed. Because slowness makes people angry, right? You don't want your service to be slow. So time is money, remember that. So here, bubble sort is O of n squared, which basically means the worst it can possibly perform is n squared operations, where n is the number of numbers we're sorting. So it's very easy to code, because the flipping thing is actually extremely easy to code, but it's not efficient at all. It's almost like baby's first sorting algorithm. So to show you how easy it is to code, that's all of it. That's all that you would need. So we don't need to decipher what this actually does, but we can see 6 lines of code. This is bubble sort. That's all it takes. It's tiny, right? So it's easy to code. I could do this.
So
Really
that's
easy.
just, you refer to that as a code.
Yes, this is actually Python. There's different types of programming languages. You have C, C++, Python, Java, a bunch of different languages. Python is my favorite language. It's also the language a lot of people learn first. But this is a programming language, and this is how you would do it in Python. You can see it only takes 6 lines. Pretty easy to code. But if we're Facebook and we're going through piles of people 1 billion numbers tall, we can't do this. So this brings me to, well, we can do something better than O of n squared. We can do something better than an algorithm that takes 1 trillion operations if our list is 1 million numbers long. So that brings us to merge sort, which is the second thing I showed you with the cards. So let's take, and I promise I'm pretty sure I did this one right. So let's take the same list as last time, 4, 16, 7, 0, 13, 2, 22, right? Let's take the same list as last time. And first we're gonna split it up. So let's split this list up into camps. So we have here the green camp. I hope that's clear to you guys. We have the green camp and the yellow camp, right? Okay, cool. Let's do it again. So now we have the green camp, the purple camp, the yellow camp, and the red camp. If this list was 16 numbers long, there would have been 16, and then 8, and then 4, and then 2, and then we stop. We stop once the camps at the bottom either have 1 or 2 things in them. We stop when these camps or groups of numbers are either size 2 or 1. So we want to split this up over and over and over again into tiny little fragments. So we stop splitting once the fragments once every single fragment has either 1 or 2 things. So that's how it'll go. It'll either be 1 thing or 2 things. In this case, I purposefully made this list to have 8 numbers in it, because 8 is a power of 2, which means when we split it up this way, it'll be very clean. We have 4 sets of 2. If I had made this size 9 or 10, we would have had 2, 2, 3, no, we would have had like 2, 2, 1, 2, 2, 1, or something like that. So I made it a list of size 8, so that once we fragmented it, it would be clean. Cool. So now we have these camps. So now what do we do? So now it's almost a little bit similar. It does the same thing as the bubble sort, the flip, but this is super easy. So we're going to flip each one of these camps depending on whether or not they are already in order. So if we take a look at this, we can see the green camp was already in order. This is fine. The purple camp was 7, 0, which is out of order. So we turn it into 0, 7. The yellow camp was 13 and 2, so we flip it, it becomes 2 and 13. And finally, the red camp is 20 and 2, so we flip it, it becomes 2 and 20. Okay, so there is a better way to do this. when I sit down and code merge sort, this is how I do it. It's not the most efficient way. But we started with the split. This is the flip part. And then finally we get to merging everything back together. So remember that conveyor belt analogy. So let's focus. For now, we're going to focus specifically on these two camps here, the 4, 16, and then the 0, 7, the green camp and the purple camp. So here, we have two camps. We're at some factory and there's a bunch of numbers coming down a conveyor belt. So first I'm going to grab the 0 box because it's the thing in front of me. I'll put it there. Then I grab the 4 box and put it here. Then the 7 box and put it here. And the 16 box and put it there. So again, think of it as there are two conveyor belts in front of you with numbers that are already in order. You're just grabbing something from a conveyor belt depending on which one is smallest. Does that kind of make sense? So it's how we start with these two camps and end up with them in order. This conveyor belt analogy. Cool. So now we have two camps. We'll call them again the green camp and the purple camp. So here, I just went ahead and I put the purple camp in order. So this was, I think, like 13 to 22 or something. So I just put it in order to be 2, 2, 13, 20. So again, we have our conveyor belt. So first we're going to grab the 0 box, and then the 2 box, and then the 2 box from here again. And then the 4 box on the left, and then the 7 box on the left, and then the 13 box on the right, the 16 box on the left, and the 20 box on the right. And we ultimately get it back in order. There you go. So now again, if this was a size 16 list, if I had started with 16 numbers, we would have to do this again. So now we would have 8 numbers that are in order, and then we would have another 8 numbers that are in order. And again, we would do the conveyor belt thing. So grab the 0, grab the 2, grab the 2, grab the 4, grab the 5, grab the 7, so on and so forth, until your boxes are stacked in order. So the beautiful thing about merge sort is it's a lot faster. How much faster? Well, let's talk a little bit more about time complexity. So, oh, I screwed that up a little bit here. That's totally fine. Yeah. Merge sort. So here, merge sort is going to take a smaller amount of time than bubble sort. So before, have a good day, by the way.
You too.
I think this should work. Okay, I just hope this works. So before we had n squared. So if we had 1,000,000 numbers in our list, we'd have to do 1,000,000,000,000 calculations. Or if we had 1,000 numbers in our list, it would do 1,000,000 operations. Here, we only ever have to do n times log base 2 of n operations. So that's a little weird. But does anybody remember studying logs in high school? Yeah, so in computer science, when I say log of something, it's a little different than if I say log in math. So in math, if I just say log with nothing in front of it, it's log base 10. In computer science, it's log base 2, but that's its own thing. What does it mean? So log base 2 of something, let's say x, log base 2 of x is asking the question, how many times do you have to multiply 2 by itself to get to this number? In other words, what power do we need to raise 2 to get to this number? So for example, we have log base 2 of 8. So we know 8 is 2 times 2 times 2. So it's 2 to the power of 3. Yeah, it's 2 to the power of 3. So log base 2 of 8 is 3. 16 we have to do 2 times 2 times 2 times 2. So log base 2 of 16 is 4. Then log base 2 of 32 is 5, log base 2 of 64 is 6, so on and so forth. So a million isn't actually that far away. Just think about it. We go 1, 2, 4, 8, 16, 32, 64, 128, 256. It just keeps getting bigger. 512, 1024, 2048. And this is just going to keep doubling. So if it keeps doubling and doubling and doubling, it's not going to take very long for this to get to a million. Turns out you need to take 2 and raise it to about 19.9. So you have to multiply about 20 2's. So if you say 2 times 2 times 2 times 2 times 2, 20 times, you'll get something that's a little bit over 1 million. Okay, so that's log base 2. So log base 2 of a million is only 19.9. So here, instead of doing n times n, which is what we would do if it were n squared, we're only doing n times 19.9. So instead of it being 1 million times a million, it's going to be 1 million times 19.9. So if we have a list with a million numbers in it, and we use merge sort, it's only going to take 19.9 million operations, which on that same computer I mentioned earlier, that would have taken 2 seconds. This will take no time, a microsecond. So as this gets bigger, so for example, instead of a list with a million, you have a billion numbers. That equation, n log n, will keep getting bigger and bigger. Inevitably. So if we have a quadrillion numbers in a list for some reason, this is still going to take a really long time. But if we compare it to how it would have performed using bubble sort, it's always better. Because remember, bubble sort, we have n times n. With merge sort, we have n times something that will be smaller than n, much smaller. So it's much more efficient. It's more difficult to program, but you're able to get through lists much faster than you would have if you were using bubble sort. So I just showed you 2 algorithms, and I didn't even really show you everything algorithms can do. I just showed you sorting algorithms. There are entirely different algorithms for questions like, for example, if I'm booking a flight from New York to Los Angeles, what is the cheapest flight I can get? So if I go online and I'm looking for a flight from here to LA, Google's just going to recommend me the cheapest flight possible. So that could be here to Denver to Los Angeles, or it could be here to Detroit to Denver to Los Angeles, or it could just be here to Los Angeles, right? But the question is, how does Google know which is the cheapest? Does it look at every possible combination of flights that lead to LA? No. It does something smarter, and this is what we call a graph problem. When we want to get from point A to point B with the cheapest budget or the smallest distance, how do we do that? So that's a different type of algorithm. Yeah.
Isn't the day of the week another factor?
Yeah, it is. It is. So if I'm flying on a Tuesday, it'll probably be cheaper than if I were flying on a Saturday. There's many different attributes that go into that, which further complexifies the problem, right? Google's able to just handle that in a microsecond. Some engineer at Google sat down and just did this, right? So how did they do this? Stuff like this. They didn't use merge sort because merge sort isn't relevant in that problem. There, they probably used some different algorithm, a graph traversal algorithm. But that's effectively what algorithms are. They're not a program. You don't download an algorithm from the internet. It's a lot more like a cookbook. It's a set of instructions to make your programs faster. And ultimately, when it comes down to it, a good programmer, a good software engineer knows good algorithms and employs them regularly. So that's today's lecture. If you guys need any tech help, I'll be here for a little bit. Other than that, I will see you guys hopefully on Monday.
Thank you.
For sure.
Remember last year, I suppose it was a trip,